Okay, we're going to begin Chapter 2, and Chapter 2 is a chapter about reasoning, and it leads into organized proofs, and we'll get into that in the next chapter, but this is kind of how you lay it out, is you have to understand the process of reasoning. And I like to think of reasoning as just organizing your thoughts and coming to valid conclusions. So, one form of reasoning is called inductive reasoning, and we're going to take a look at what this is. But first, I want you to tape down your notes in your interactive notebooks, and you should have gotten a tab for Chapter 2. If not, make sure you get one from me. And we're going to fill in some notes here. So the first thing I want to do is just define what is inductive reasoning. And it's just a method of reasoning which arrives at logical conclusion by studying a series of particular examples. Now, you've done this most of your life, and you just didn't know it was called inductive reasoning. For example, when you learn to eat food, you come to the conclusion that it tastes good, and so you eat more and you grow and things like that. So this thought process is not new to us. Maybe the words are, maybe the formality of this inductive reasoning, maybe that's new, but it's something that you do every day. 3 steps take place in this process. One is you're going to look for a pattern. Number 2, you're going to make a conjecture, and we'll define that word as we go. And number 3, you're going to prove the conjecture or find a counterexample. So if you don't understand these last 2 steps, that's okay, because maybe you're not familiar with these definitions. But by the end of this lesson, you should be okay with those 2 words. All right, so let's take a look at a couple examples. And in these 2 examples, we are given a situation, and we're going to come to a conclusion based on this situation. So let's read this together. Holly has 3 different encounters with Chinese restaurants. The day after eating at each restaurant, she ends up with food poisoning. So Holly is invited to, let me see if I can do this right, Minghua, don't laugh, by her friends, but she declines the invitation, saying Chinese restaurants. And she's going to say something based on her experiences. And so if we look at what she says, it makes perfect sense. Basically, the conclusion that she has come to is that Chinese restaurants serve contaminated food. Now, we know this isn't true, but again, inductive reasoning is a process after following patterns coming to a logical conclusion. And Holly has encountered food poisoning every time she's eaten at a Chinese restaurant. So there you go. The second example, we have a bag of cookies, and 3 cookies are withdrawn from the bag, and each one is a chocolate chip. So the conclusion is, based on the pattern, that all the cookies in the bag must be chocolate chip cookies. All right, let's take a look at this word conjecture. Now, this might be a word that you have seen before. It's pretty popular in science, and let's define it. It's a statement believed to be true based on inductive reasoning. So after looking at patterns, you make a statement about it, just like with the situation with Holly. The statement was, her conjecture was, that Chinese restaurants serve contaminated food. Right, so again, in this process, we look for a pattern, we make a conjecture, and from that we can maybe come up with 2 more terms or items in the pattern. So upon inspection, as we look at these numbers, we see that each number as it progresses is just increasing by 5. And so the conjecture would be that each term is 5 more than the previous term. And so the next 2 terms in this pattern would be 12 and 17. In like manner, as we inspect these angles, we see that they are diminishing by half. And so the conjecture would be that the measure of each angle is half the measure of its previous angle. So the next 2 angles would be half of 45 and then half of 22 and a half. And so this is what inductive reasoning is. So in this example right here, find the next three numbers in the pattern. So we're just going to inspect, and we're going to make a conjecture. What do you notice? Well, these numbers should be familiar to you. They're perfect squares. And so let's see if we can come up with a conjecture. Okay, so did you say that it was, hang on, got a dog barking. Okay, you just met my dog Poppy, and Poppy barks occasionally, and so at any rate, he just was saying hello. Let's get back to this, all right? So the conjecture would be that we are taking each number and subtracting 1 and then squaring it. And so the next numbers in the pattern would be 36, which is 6 squared, and then 5 squared, and then 4 squared. Okay, and now let's take a look at the word counterexample. A counterexample is basically a way to show that something's not true. So to show that a conjecture is false, you only have to find one example in which the conjecture is not true. So again, in Holly's situation with the Chinese restaurant, we could come up with many examples in which her conclusion was not true, or her conjecture was not true. So let's take a look at these statements. So if we have two angles that are acute, then the sum of their measures equals the measure of an obtuse angle. Okay, that's the conjecture. Now all we have to do is to determine whether or not that's true or false. So can you think of two angles whose sum is not an obtuse angle? Doesn't take long. So there you have two acute angles, and their sum is 35 degrees, and 35 degrees is not obtuse. And so there's just one counterexample, so now we can say that this conjecture is false. All right, number 2, the following inequality is always true. Boy, you better be careful where it always says always, because you know there's always, all you have to do is find one counterexample. All right, so n is a positive number, so that when you square that positive number, it's going to be bigger than the number itself. Now that's pretty logical. It would seem like that would be true. But let's see if we can find a counterexample. So I'm going to start just playing around with some numbers. I'm going to choose the number 2. When I square it, is it bigger than the 2? And the answer is yes. What about 3 squared? Is 3 squared bigger than 3? Yes. And I could keep going. I could say 7 squared is 49, and 49 is bigger than 7, and so on and so forth. So going in the big number direction, I'm not going to be able to find a counterexample, so let's go in the other direction. What about 1? When I square 1, is it bigger than 1? Don't think so. Let's try to find even another one. What about 1/3? When you square 1/3, what that means, folks, is that you have 1/3 times 1/3. That's 1/9. 1/9 is smaller than 1/3. So these are just two counterexamples, and so this conjecture right here is not true. All right, so that concludes this lesson, and we'll pick up from here in class, and we'll see you then. Hopefully this has made a little bit of sense to you.